Good afternoon and welcome to this webinar about microenergy storage and energy management. This is the second webinar in a series of 3 organized by the EnSO consortium. EnSO is a project supported by the Excel program. I'm Régis Hamelin, CTO of BlueMorpho, and at BlueMorpho we are working for corporate or investors to identify the next disruptors. And our mission is then to connect disruptors with the industry. As I just mentioned, this is the second webinar. So in the previous edition, we discussed about how to design with energy harvesting. So we discussed photovoltaic cells with the SOLEMS technology. We discussed also thermoelectric generators from matter and how to transform temperature difference into energy. And also how to transform a mechanical motion, water, gas, air, or mechanical rotation into energy as well. And this is the technology from NRB. If you have not been able to participate to this edition, then you can still have access to this information. The webinar has been made available from our YouTube channel. And this webinar will be also recorded and will be uploaded as well for your reference. Okay, so today, let me introduce our guest. Today we will have 2 speakers. So the first speaker today is Dr. Raphael Salot from CEA. He is the head of laboratory storage and energy microsources, and CEA is also coordinator of the EnSO project. So good afternoon, Raphael.
Good afternoon, Régis.
And our second speaker today is Dr. Peter Spies from Fraunhofer-IIS. He is a group manager of integrated energy supplies, and this group is part of the Department of Self-Powered Radio Systems. So good afternoon, Peter.
Good afternoon, Régis.
And now, before we go into the technical details, I would like to say a few words about the EnSO project. The EnSO consortium. EnSO stands for Energy for Smart Objects. The EnSO consortium is supported by the Excel program, and it's composed of 33 partners and 5 third parties over 8 countries. You have the breakdown here on my right. And then we started to work in January 2016 for a duration of 48 months. And the total investment in this project is in the range of 82 million euros. As you can see, we have the whole value chain which is present with people from the material, from the machines. We just saw the people who are capable to deliver the energy harvesting, SOLEMS, Malle, NRB. We also have the support of world-class organization, research organization, academic and research institutes. And we have also a full ecosystem of end users and exploitation, what we call the exploitation partners. BlueMorpho is part of the exploitation partners. And as you will see, we have the full, all the competencies and all the building blocks to make your smart objects fully autonomous. So what is the objective of EnSO? The objective of EnSO is really to focus on the energy source into your smart objects. In IoT, you have sensors, data processing, and data transmission. And we are focusing our effort, our resources on how to transform this sensing element into a fully autonomous device. And we are working then on what we have baptized the AMIS, the autonomous microenergy source, which can be composed of an energy harvester, a power conditioner, and an energy storage. On top of that, we build demonstrators. We cover 15 use cases, and that starts from the smart health, with miniature glucose monitoring system, pacemakers, wearable devices, can be hearable or wearable. Also industrial application in smart mobility and smart productions with asset tracking devices or tags. But we have also broader use cases with smart locks, smart meters, and also payment cards, smart payment cards, where you can integrate more features than just the payment. So this last topic will be the object of the third webinar that will be promoted later. So, and now I think it's time to enter into the technical topics, and I will hand over the microphone to Dr. Raphael Salot. So, Raphael, I need to give you the control of the screen, and now you have the control and you can start your presentation.
Okay, thank you, Regis. So good afternoon, everybody. Before moving to the description of the energy storage solutions that are developed within EnSO, I will first give you a brief overview about CEA LETI. CEA LETI is part of CEA, which is a huge French research institute with about 16,000 employees. And CEA LETI is involved in different research fields such as biology, healthcare, communication, microelectronics, optoelectronics. And for all this domain, the objective, the focus of CEA LETI is really on technological research. So the idea is really to develop new materials, new processes, new components, new systems, and to transfer them to some industrial partners. So to really to make the link between basic research and pilot line and final manufacturing. So it's really technological research. So among all these developments, CEA LETI is hugely involved in the development of new energy solutions, miniaturized energy solutions, typically for IoT devices. So I move to the slide. So it has already been shown by Regis, but I show it once again just to really to put the focus on the energy aspect, which can be a bottleneck in the development of new IoT device, because we can see that most of these devices tries to be as small as possible, and as long as you try to reduce the size of this device, then the energy block becomes really critical. So really within EnSO, the objective is to provide new components that we call AMS for autonomous microenergy sources that include both energy storage, but also energy harvesting, power conditioner, with the idea really to miniaturize all these components and then to provide an autonomous energy sources for the device. So if we move now really to the block energy storage, how do we proceed when we have to develop a new smart object and to think about powering this smart object? So first of all, what is very important is to provide to the battery designer, let's say, the main requirements to the battery. Of course, the main requirements are typically the capacity and internal resistance of the battery. And these data are provided after an in-depth analysis of the electrical consumption of each use case. So it means both the average power, but also what is very important is the peak current, because for instance, in most of the IoT device, for instance, when you want to transfer some data, then you will have some peak current, and it's also very important not only to know the average power, but also the peak current that will be requested to the battery. And then the second point that is very important is to obtain the total capacity that will be requested to the battery. And either it can be the capacity for the entire life of the product, or thanks to the combination with some energy harvester, it will be only the energy that is needed between two recharge. So it is very important to also to make this analysis. And then on top of that, we will have also to know the volume that is available for the battery. And volume means not only the total volume, but let's say decomposition between the surface and the thickness of the components. Because for instance, if the thickness is very small, then it will have some dramatic impact on the choice of the energy storage components. So based on that, when we have a look to the main requirements of IoT devices, we came to the conclusion that not only one energy storage technology can fulfill all the requirements. And based on that, we developed within EnSO, in fact, 2 lithium battery technology to address most of the IoT smart object energy requirements. So these 2 lithium battery technology are all based on the same physical principle, meaning lithium chemistry, and in a battery, typically, that's what you can see here on the schematics on the top. You have 2 electrodes, and in between 1 electrolyte. And when you charge the battery, for instance, you have a lithium battery moving from 1 electrode to the other one. And then when you discharge the battery, the lithium makes the opposite way. So what are these 2 lithium battery technology we developed within EnSO? The first one, we call it inorganic microbattery, and the second one, polymer microbattery. So a brief description of both of them. Inorganic microbattery means that we use only inorganic material. There is no liquid, no organic or polymer material within the stack. And to obtain that, we use some manufacturing that are very close to what is used in microelectronics, meaning the process are film depositions under vacuum, so typically sputtering. And then in order to have very small and miniaturized size and surface, we also use typical patterning methods that are used in microelectronics, so photolithography, laser patterning. And thanks to that, you can obtain some very, very tiny device, so with surface down to a few square millimeter, also very, very thin thickness down to 100 micron. And the typical range of the capacity we target with such technology is between microamps hour and milliamps hour. On the other side, the polymer microbattery technology. So in this case, the electrolyte is a polymer electrolyte, so also a kind of solid state, but polymer, not inorganic. And in this case, the manufacturing is more similar, let's say, to standard battery manufacturing, meaning ink deposition on metal foil, induction. So classical, let's say, deposition methods. And for this kind of technology, we typically obtain some components of a few square centimeter, also very thin, but let's say a little bit thicker than the inorganic microbattery technology. So the minimum thickness achievable is, let's say, about 300 microns, but it can be, let's say, between 300 and 500–600 micron thick. And for this kind of technology, the target for the capacity is a little bit higher, so typically milliamp per hour up to a few tens of milliamp per hour. So then I will go a little bit more in detail and give some examples of the 2 technology. So first, the solid state inorganic technology. So here you have an example of a component. So you can see on the left the manufacturing of these components that are done on 200 millimeter silicon wafer. So typically on such a wafer, you can have about a few thousand, from 4 to 10,000 components. And then all the batteries on the wafers are diced and thinned. And then you can obtain this kind of components. So in this case, here on this examples, you have a battery of 1.7 by 3.1 square millimeter with a thickness of 100 microns. So very, very tiny and very, very thin, and with the capability to be integrated in a very small system. So in the next slide, you will find again some picture of different components. So some batteries on silicon, and then some battery also packaged in standard microelectronic package such as BGA, LGA, or QFN. You can see also here on this picture that this kind of batteries can be manufactured not only on silicon, but it can be also manufactured on glass wafer if needed. And here you have just some bullets summarizing the added value of such technology. So really important, the safety, reliability due to this fully solid state inorganic materials. I've already mentioned about the thickness, the size, but also what is important is the temperature stability up to 250 degrees C, and also a very low self-discharge, so which can be lower than 3% per year, which is very, very good for rechargeable battery. I will now move to the polymer technology. Which is you have a picture here of such components. The interesting point compared to the previous one is the cost manufacturing, because the vacuum process can be a high cost process, which is not the case of the manufacturing that is used for this kind of batteries. The energy density is also very, very high because it is based on metallic lithium, which is quite good for the energy density. It is also very safe since there is no organic solvent that is used. And you can see here an example of a battery that is cut and that is still working, not for a very long time, but still working and not leading to some risk regarding safety. And then regarding temperature, we can have a compatibility up to 150, which is a little bit lower compared to the inorganic technology, but much higher than the standard lithium battery technology. And here you have some rough results and value regarding the performances of such components. So you can see that we can reach capacity of a few milliamps hours for these designs, and with some pulse capability up to 10 C. So my conclusion is that within EnSO, with all the consortiums at EnSO, I think we offer a quite unique offer regarding energy storage solutions that are really designed to meet IoT requirements. And really, if you are interested, if you have detailed questions, feel free to contact us, either to discuss or to have specific evaluations of our solutions compared to your needs. And also, you have also to know that we offer the possibility to test and evaluate the EnSO solution.
Thank you very much, Raphael. That's a very interesting and very helpful presentation. So there will be questions at the end of the second presentation, but I would like to say to the audience that if you have any questions you would like to ask, you have a specific box for that. So don't hesitate, shoot your questions and we will manage that at the end of the presentation. So now we're going to move to the second speaker today. So I would like to welcome again Dr. Peter Spies from Fraunhofer-IIS, and I will give you as well the control of the keyboard and the mouse, and you can now start your presentation.
Okay, thank you, Régis, and good afternoon to everybody. Yeah, so before I start with my presentation, I like to spend a few words about the Fraunhofer Institute for which I am working. We are the Fraunhofer Institute for Integrated Circuits. We were founded in 1985. We have around 1,000 employees. We have 15 locations in 11 cities. The headquarter is based in Erlangen, and me and my team, Integrated Energy Supplies, is based in Nuremberg. So the guiding topics of the Fraunhofer-IIS are cognitive sensor technologies and audio and media technology. On the field of audio and media technology, we develop coding systems. We work in the standardization of audio and image coding. We also deal with production tools, post-processing, as well as audio signal analysis and processing. On the field of cognitive sensor technology, this is actually the topic where our department, self-powered radio systems, is belonging to. Here we are developing sensors and integrated circuits. We're developing communication technologies, but we are also dealing with the analytics, and we finally are also developing services and business models. So to start with the topic of today, I like to give a little bit of motivation for the technologies we are developing in the EnSO project. As you all know, wireless IoT application like sensors, microcontrollers, or radio systems typically work in burst mode, which means they process or send data only in very short time slots. And this is the reason we also need batteries, because these small batteries provide the energy to power the microelectronic systems. Typically, we have rechargeable battery, as my colleague Raphael already explained. And these batteries have a limited operation range in terms of voltage, current, and temperature. So you have to be very careful when you charge them and when you discharge them. And furthermore, if we are dealing with energy harvesting uses ambient energy like light, thermal gradients, or vibrations, but energy harvesting provides only small amount of electrical energy. And this is the reason why we need power and battery management electronics, so that we can process the different power levels from the different harvesters, and so that we can control and monitor any kind of storage devices like rechargeable batteries. So one challenge in micro energy harvesting and micro power management is that the energy transducers used in energy harvesting, like thermoelectric harvesters, solar cells, or vibration harvesters, provide only very small voltages and only very small currents. And this is the reason why we always need a dedicated power management, so that we can adapt the current and voltages from the transducer, store the energy in the battery, or provide the power to any kind of application. Another challenge in micro power management is that depending on the application, there might also be some higher voltages or higher currents. So for example, if we have full sunlight on a solar cell, or we have a large thermal gradient on the thermoelectric harvester. So we need a certain operation range for the power and battery management circuits to be able to process the maximum power from the harvesters. And finally, as I already mentioned, we always work in burst mode, so we need large current peaks to power the RF transceiver during transmission. And so to achieve a maximum efficiency and a maximum lifetime of the battery, the currents and voltage levels have to be limited. One first example I like to show you in this webinar is a certain DC-DC converter, which is optimized to work with very, very low input voltages. Such low input voltages might come from thermoelectric harvesters at very low thermal gradients or from solar cells if they do not have much illumination. This is a DC-DC converter which can work down to 30 millivolts without any additional startup voltage, and with such a circuit we are able to process very small amounts of energy from thermoelectric harvesters on solar cells. It also has a decent efficiency. As soon as we get higher input voltages, the efficiency of the harvester is increasing and we get even more power from the harvester. This is an example where you see actually the power output as a function of thermal gradient. The most important thing if you're dealing with thermal harvesting is that you always have to need some kind of heat sink to keep the cold side of the harvester cold. And so your power output does not only depend on the thermal gradient, it also depends on the size and on the volume of the harvester. So if you could afford a larger heat sink, then the thermal difference on your thermoelectric harvester is bigger and then you get more power out of it. Another example for a dedicated power management system for a special harvester is this one here on this slide. It is an AC to DC converter for vibration harvesters. So vibration harvesters use any kind of vibrations coming from machines, motors, vehicles, but they produce alternating current. And so for that reason, you at first need some kind of rectification to transfer the AC voltage to a DC voltage. Then you need some kind of filtering, some kind of control, and then you are able to provide a DC voltage to charge your battery or capacitor or to supply your load. So further on, if we go a little bit from the power management to the battery management targets, a certain battery always has a given charge profile. This means you should control current very precisely to be able to charge the battery in the most efficient way. So typically lithium-ion batteries need a so-called constant voltage, constant current charge profile. This means, as you can see it here on the diagram, at first you have to use a constant current until you reach the maximum cell voltage. And if you have reached the maximum cell voltage, then you have to reduce the charge current to keep the cell voltage constant. And to apply, to generate such a constant current, constant voltage charge profile, it is needed that you use some kind of specialized regulators. A very simple form of a regulator is a linear regulator, which you can see here on the block diagram. That's just a voltage control loop where you have an input voltage and an output voltage. And by choosing these two resistors in a proper way, according to that equation here, you can control the output voltage independent on the input voltage. So whatever voltage comes from your harvester, if you control that two resistors, you can decide on the precise charge voltage of the battery. But typically we do not need only to control the voltage, but as you have seen in my first preceding slide, you also have to control the current. And for that reason, in a typical charge regulator for a lithium-ion batteries, you have three control loops. Here in the middle, you see the control loop for the voltage, which controls this transistor depending on the output voltage. We have another control loop here where we can measure the charge current, and depending on the level of the charge current, this transistor is controlled here. And with these two voltage levels, loops, you are able to control this charge regime, this charge profile, and you are able to generate this constant current, constant voltage charge profile. Finally, since some lithium-ion batteries are very sensitive to temperature gradients and to high temperature, you need an additional third loop to monitor the temperature of the battery, and in any case to avoid charging when the battery is too hot or too cold. So another important feature of power and battery management system is IoT application is the feature of battery monitoring. This means that we have some kind of circuitry which is able to estimate the charge which is presently charged in the battery. This this technology is typically called state of charge estimation. And in the state of charge estimation, you typically measure the charge current, you measure the discharge current with the help of a small resistor, and you have two registers which you can increase or decrease, and depending on how much charge is flowing onto your battery or how much charge is flowing from your battery, you can increase or decrease these two counters, and the number of these counters is then a value for the estimated charge on the battery and for the estimation of the energy which is available in your application. The challenge with such a system is that it needs a lot of electronic components, and often this might be too power hungry for a very low power application like an IoT sensor. And for that reason, in the EnSO project, we used and developed a special form of SOC estimation, which just uses the open cell voltage of the battery and which just uses some simple comparators to just make a very rough estimation of the state of charge depending on the open circuit voltage of the battery. Here you see the open circuit voltage, and the open circuit voltage is also a function of the SOC of the state of charge. So the higher the voltage of the battery, of course, the higher is the SOC. Here you see a typical circuit diagram where we have implemented 4 different steps to estimate this state of charge. And here you see in green the voltage of the battery, and in red the output of this SOC circuit, which is able to give you a very rough estimation, but it needs a very low power itself, so it's very optimized for low power IoT applications. So this is actually an overall system where all the different components I've talked today are used, and a couple of components more. This is actually a multi-source energy harvesting system. This means you can connect to this system thermoelectric harvesters, solar cells, and also electrodynamic harvesters. And you can charge a battery or a supercap, or you can also get any kind of information about a state of charge of the battery or of the supercap. There are some applications where it's really beneficial if you are able to use not only one harvester, so you are able to use energy from different kinds of ambient energy sources. So in the EnSO project, for example, we're developing a system which is used in the railway application where we combine solar harvesting with vibration harvesting. We're also working on an application where we combine thermal harvester and vibration harvester, which is very good suited for any kind of industrial sensors. And a further combination of 2 different harvesting types might be wearables, where you can combine solar modules with solar harvesting. So with the last slide, I like to summarize my talk. So energy harvesting systems always need power, dedicated power management circuits for maximum efficiency. The goal of the battery management is to control the charging of the battery and keep the battery in a safe and efficient operation mode. In the EnSO project, we developed a multi-source energy management system which can work with different kinds of harvesters and can manage different kinds of energy storage devices. So if you want to discuss any kind of application, or if you are interested in any kind of cooperation, do not hesitate to contact us. Thank you very much.
Thank you very much, Peter. So again, message to the audience, you can now start to send your questions, and we're going to open the discussion now. My first question will be to Raphael. So Raphael, you showed us two different kinds of batteries. And do you think that there are one battery for one application, or how do you split the different applications between the two batteries?
Let's say that what we've seen with the different end users that are involved in the EnSO project is that you are right. We can divide the applications with associated with the two different technology, and let's say that the polymer technology appears to be very well suited to application domains such as asset monitoring, gas network monitoring, smart wearables. So meaning some applications where you need at least a few milliamps hour up to a few tens of milliamps hour, and where you need to have small devices, but let's say you can admit thickness of few hundreds of microns, and also where the cost is also very, very important. And on the other side, what we see is that the solid state inorganic technology is very well suited to all medical applications, typically implantable medical applications such as pacemaker, but also hearing aids. And we have also some demands on other implantable devices. So yes, you are right. We can make a kind of split between the applications for the two technologies.
Mm-hmm. Yeah, the very miniature is more for the implantable devices require highly miniaturized devices indeed. And so could you also comment about the temperature range, the working temperature range? We know about lithium and the problem with temperature. So can you give us more details on that?
Yes, so there are, regarding temperature, there are two aspects. There are the, let's say, the temperature compatibility. So without operating at this temperature. So for the inorganic technology, we can go up to 250 degrees C, which is quite interesting because it becomes compatible with the solder reflow interconnection processes that are most of the time used for the connections of microprocessor, IC, and so on. And for the other technology, it's more in the range of 100 and maximum 150 degrees C. Then regarding the operating temperature for the polymer technology, it's standard to classical batteries, so up to 50 degrees C. And for the other technology, it can be possible to cycle at much higher temperature, let's say higher than 100 degrees C. The edging in this case will be a little bit higher. The number of cycles will be decreased, but still possible to have some behavior at this high temperature.
Yeah, that's accelerated aging at high temperature. Okay, that's a conventional physical problem. Okay, and you mentioned in your presentation that in the EnSO project we are open for collaboration. So that's, I think, something kind of unique in European projects. We are open to work with external partners, and we can supply some samples. That's right.
Yes, that's right. So during the project, we define a different kind of AMS, autonomous microenergy sources, And so some of them are very specific to each end user, but we have also developed a kind of generic products, so that includes battery, NFC, and the power management and connection possible to other energy harvesting solutions. So we are open to testing these components with other partners. So once again, feel free to contact us.
And we can also provide design support.
Yes, that's also very important, because each use case needs to be an in-depth analysis. And it's important to have competencies both on energy storage, energy harvesting, power management, and we have all this competency in the projects, and we can gather all this support and make some design support. Yes.
Yeah, and the good news is that we want to maintain this working consortium beyond the EnSO project. So we want to become a resource for anyone who wants to develop an autonomous solution. Okay, so let's move to Peter now. So you mentioned that there's multiple questions. I have multiple questions. You mentioned that you have first to decide between DC to DC, AC to DC. So that's the first degree of decision. And then there's an energy source. You mentioned temperature or vibration. And then there's a third one, which is the battery management. So that makes lots of complexity, lots of diversity. So do you think it's possible to have just one chip working for all these use case, or do we need a full range of devices?
Of course, this depends on your application. Of course, the most efficient way is to focus only on one kind of harvesting system and to optimize that for your use case. But of course, there are a lot of applications where you sometimes have only one source of energy and sometimes only the other one. And so you can work with the combination and of course achieve more system functionality.
Okay, and what are the typical power levels that we can expect from energy harvesting? Because we have seen that there are plenty of options.
Yeah, so we start with power levels down to the range of a couple of microwatts. So the problem is that the processing, the power management circuits do consume a certain amount of power or current by themselves. So as low as 1 or 2 microwatts, we can start harvesting energy. And then to the upper level, there is actually no limit. We have applications where we harvest a couple of milliwatts, and we can also harvest a couple of watts. Of course, that depends also on your application and on the environment. But the lower level is in the range of microwatts.
Mm-hmm. And can you give examples of applications that you have seen in your experience with energy harvesting? So
yes, of course.
Microwatts and macrowatts level, what can we do with that?
Okay, so for example, we have one application where we power Bluetooth low energy, and for Bluetooth low energy, we need around 100 microwatts. And if we have that energy available, this is, for example, possible with a thermal gradient of 2 or 3 kelvins, we can generate 100 microwatts, and that's sufficient to measure and transmit a data once per second. Another example, once per second. And another example from a higher power level is, for example, an application where we use vibration on trains. There we're using vibration harvester, where we are able to harvest 10 milliwatts of power, so 10 milliwatts. And this is then sufficient to power GPS and UMTS once per hour. So you can measure the precision of your train, of your container once per hour and transmit to the cellular network once per hour.
Okay, so yeah, it's interesting to see that if you just have 3 degrees of difference of gradients, you can already send a Bluetooth message every second. So that's a very, very impressive result as far as I'm concerned. So you mentioned also the solar harvesting path on the multi-source energy harvesting system. So there are quite a lot of switches on this circuit. So could you comment on that?
Yeah, that's a really tricky part, because we found out that the most efficient way of charging the solar energy to a battery is by a direct connection. So because all these DC-DC and AC-DC converters do consume a little bit of power by their own, and of course, if you don't need them, that's even better. But that's only working if the output voltage of the solar cell is matching to the input voltage or to the voltage range of the battery. So for example, if your solar cell is producing exactly 4 volts, a little bit below, a little bit above, and your capacitor or your battery has the same voltage, then it's very easy. You do not need any voltage adaptation. And for that reason, in such a case, we are able to disconnect the whole DC-DC converter, feed the power directly to the battery, and are working in the most efficient way because we do not have any losses with the DC-DC converter. And this is the reason why we use these switches. So in that certain aberration range, when the solar cell is matching directly to the battery, we do not need this DC-DC converter and self the power consumption for that component.
Okay, I see. In fact, you mentioned it multiple times, the power consumption of the circuit itself is critical. So for this last circuit, which has multi-source energy harvesting, which is probably the most complex one that we did in the frame of EnSO, can you comment on the power consumption itself here?
Yeah, the power consumption depends on the application. It should be also in the microwatt range. But actually, this system is not a system which is really going to a real product. It's more some kind of evaluation board where you can experiment with different harvesters. For that reason, we also have current sensors combined with each harvester so that we are able to monitor the current from the single harvester, investigate their power output in a certain use case, and then we can use these results to decide really which harvester is most beneficial in a certain application. And of course, then we would reduce the complete design and just leave the components which are really required in the end user product.
Okay. I have one more question coming from the audience, and this question is, can we use energy harvesting to top up or extend the lifetime of a larger battery? And the example which is given here in the question is a battery, a lithium-ion battery, rechargeable battery of 500 milliamp hour. So who wants to comment on that? Peter, maybe?
Yes, of course, I can comment on that. That's actually what we are doing here in applications where we need a higher power. So for example, we have a GPS tracker, and this has a battery of 2 or 3 ampere hours capacity, and we use additional harvesting to assist this battery to just extend the lifetime of the lithium battery.
Okay, and what is the power consumption of this use case? Maybe you can comment on that.
The power consumption is typically between a couple of milliwatts. So I think we start at 2 or 3 milliwatts. If we have very low numbers of position measures per hour, and it goes up to several hundred milliwatts of power.
Mm-hmm. So basically the answer is yes, it is possible. We have seen lots of use cases where energy harvesting is used to supplement a first energy source. We mentioned at the very beginning of this webinar that we can have some boost of needs for boost of power. For example, when you send a message, when you collect data, then you are in a given working working conditions. And when you send the information, then you need a boost of power. And this boost of power can damage, in fact, the battery. So you need an energy harvesting, a supercap, or a micro battery associated with that to be able to supplement the current energy source. So yeah, this is typically the kind of use case where we can give our support or our expertise. So don't hesitate to contact us and to reach out and discuss your case. We will be more than happy to discuss with you your problems and maybe find some solutions. Okay, so I don't see much more questions from the audience now, so I think that we're going to move to the conclusions. So I want to thank you again, Raphael and Peter, for giving us your advices and making these presentations today. This was then the second webinar in a series of 3. And the third webinar will be on the demonstrators itself. The first webinar was on energy harvesting. Then we moved to how this energy could be stored and managed. And for the next and final webinar, we will have the opportunity to discuss the use case scenarios, and we will give you more details on the demonstrators which are working autonomously in the EnSO product. So follow us on our LinkedIn profile, on our Twitter accounts if you want to participate to the next webinar. And again, this presentation is recorded and will be made available from the Blue Morpho YouTube channel very soon. So thank you again, and have a great afternoon and a great weekend. Bye-bye.